morning to all of you, and my sincere apology that I could not come there because of some official responsibility here in my institute, and also because of some of my other health-related issues. But anyway, thanks very much for giving me an opportunity to present. So, can you go to the next slide? So, we'll present it in a two different ways. This is the outline of our talk that just since this is related to the quantum NLP, I have to give in one or two slides a brief overview of Indian NLP, and then the talk is mainly related to the affective computing, particularly the multimodal affective computing. So I'll give you a brief introductions of motivation and background, and then some of the techniques that we had developed earlier, particularly for solving this problem of emotion recognition, sentiment analysis, designing the multitasking system for sarcasm detection, emotion recognition, and sentiment analysis, and then how gradually we are also moving to the quantumized version of these models for solving this kind of issue. So we'll discuss. We'll try to wrap up in 1 hour. To begin with, so next slide. Please go to the next slide. Okay. Yeah. So this is how our Indian NLP, any NLP appears. So if you see that on the left part there are the different layers of NLP that all of us knows that start with morphology, then there are part of speech tagging, then there are chunking, parsing, then there are semantics, discourse, and coreference. And if you go in the lower to the upper part, so the complexity actually increases. So that means if you are solving a problem at parsing, maybe it is harder problem than chunking. If you are solving a problem of discourse and coreference, so this needs more information from the lower level. That means the semantic information, that needs the information from parsing, chunking, use tagging, or the morphology. But also the information always is not unidirectional. So that means it is not the case that if you want to do the semantic analysis, the chunking or parsing are needed, that appears, but it may also happen that if you want to resolve the semantic ambiguity, sometimes the parsing information is also useful. So that means, and also in the reverse direction. Okay? So that means that parsing ambiguity, if you want to resolve, that may require the semantic. So the information flow in this pipeline sometimes is bidirectional. Okay, that's the upper layer requires the lower layer information, but also on the other hand, the information from the upper layer may be required to solve a problem of the lower. On the right side, you see that there are 3 dimensions. In one dimension, there are different languages. One dimension, there are different algorithms, and in one dimension, there are different problems. Right? So we can represent the natural language processing with respect to this as a kind of triplet, where one side represents a language, other side represents the way one side represents the problem, and another dimension represents a specific element. So that means if you really want to solve, let's say, part of speech tagging for Hindi, you might have to select an appropriate algorithm, either hidden Markov model or conditional random field or any deep neural network. What kind of algorithm is more promising or more suitable, more appropriate for solving this problem that you have to. Now going forward, so with this background, if you look into the Indian situations, that India is a multilingual country. So Arpan, you should go to the next slide. No, Arpan, please go to the next. Arpan. So India is a multilingual country with different languages spoken in India, and these languages are derived from the major streams like Indo-European, Dravidian, Sino-Tibetan, Austro-Asiatic, and many of the languages are spoken by the large number of population. For example, Hindi can be ranked as a third language. Bangla is spoken, Bengali is spoken by a large number of population. Then Urdu, Marathi, Tamil. So there are many speakers for these kind of language. So go to the next slide, please. You see that in India we have 22 official languages, and as per the Indian Constitution, but there are 122 major languages. There are almost 1600 regional languages, 13 states, 720 dialects, and almost 30 languages are spoken by more than 1 million native speakers. And 120 languages are spoken by 10,000 people. But ultimately, this 20% of the people knows English, can understand English, but 80% cannot. So there is a necessity to build language technology solutions that can bridge this language barrier between the different people. Okay, so that is the reason NLP technology is extremely important, particularly in a country like India. So I can go to the next slide. Now, this talk is basically related to the affect, and let's define that what we mean by the affect and the affective computing. Okay, so go to the next one. Yeah. So affect basically, if you see that it refers to the emotion and related phenomena, and like emotions, for example, the moods, the interpersonal stances, preferences, personality of the speaker's personality, like nervousness, anxiousness, restlessness. So all these are the notations of some kind of affect behaviors, and moreover, it can also depend on the specific cultures, like individualistic, it may be collectivist, it can be engineering versus social. So you can see that affects can refer to the emotion and all the other related phenomena that are related to this. Now, what do you mean by affect computing? In the next slide, if you see that, yeah. So if you go to the affective computing, this term that it was pursued in 1995, okay, by Raj Picard. Upon he changed the slide. In 1995, in her book, this particular terminology was introduced, and this was actually defined originally as a computing element that relates to or arises from or deliberately influences the emotion. And then you see that the computing of creation and interactions with the machine systems that sense, recognize, respond, and influence the emotions. That is what we mean by the affective computing. Okay? Now, going forward, if you look into the research of affective computing, please next slide, please follow here. So, affective computing research is not itself is the you cannot perform the research in isolation. Rather, this research is a multidisciplinary research. But please next slide, can you go? So it focuses on developing the systems that recognize or interpret or simulate human affect, that actually how it affected sensing inform machine understanding of people, or it can also attempt to make the computers behave like a human life, and also it will focus on giving the machines emotional capability. And it covers also related other topics like sensing and analysis, psychology and behaviors of the speakers, generating the behavior, generating the responses that comply with the empathetic responses. So now at that place you can consider that affective computing when we talk about. So we actually want to develop a technology, or we want to give a technology skills for making the computers emotionally intelligent so that it can interact with the people. Okay. Now we'll discuss with this background that there are two sides. One is the affective computing system, the other one is from the user perspective. Okay. On the other hand, the users, if you observe that if you want to build a emotional recognition system, that actually observe the behavior of the users. And what those behaviors are, the behaviors can be an emotion, the intent of the speakers, it can denote a particular preference of the speakers of the user, the particular facial expressions, visual expression, gestures, the physiological signals. So all these are the stimulus for building the affective computing system. Now, we have been doing this research since the last 8-9 years, and we have actually addressed varieties of problems. I'll just show you one or two problems that we have solved so far. In the next slide, please go. Yeah, so this is one model that basically two systems we developed. One was published in NLP 2018. The other one was in NACL 2019. And our goal was to build a multimodal multitasking system that can perform both sentiment and emotion analysis. Now, let's see that in the next slides why these are important, why multitasking is important, how multimodality helps. One motivating example. We pose the sentiment and emotion as a multitasking system because we see that the emotion and sentiment are very closely related. For example, if you look into the emotion like anger, fear, disgust, sad, so all are the notations for the negative sentiment. On the other hand, let's say happy is a kind of positive sentiment. So you see that there are correlations between these the sentiment dimension and the negative dimension and the emotion dimensions. And if we can build an end-to-end model that can perform both these tasks, then the complexity of the system will be reduced greatly. And why we need multimodality? If you look into this conversation and this particular utterance is taken from a particular conversation, you see that the first one is saying that thanks for putting me on hold. I have all the time in the world. Now, actually, in the gold standard data, it was sentiment actually negative. But you see that if you don't see the visual expression, or let's say the contextual information, the audio part, the acoustics of the speech, the variation when the speaker has spoken this, it is very hard to get an idea that this actually refers to the negative sentiment, because there are positive words, like thanks is a positive word, and if you look into this particular textual utterance only, the model may mistakenly classify it to be the positive sentiment. So if you want to label it as a negative based on the context, because the context says it should be negative, because the person was not in a was trying to connect to the particular person, but he was not able to do that. And that is the reason why the speaker has spoken like this, that thanks for putting me on the hold, I have all the time in the world. So in fact, the person was sarcastic in nature, and that only we can identify from the visual or acoustic information. The second example is also like this, that I'm fine. Now, fine is a good word, so it may actually, it reflects the positive emotion, let's say, but actually the emotion was sad, because the person was not in a good mood, and his friend was trying to specify his mood, and then suddenly, and the speaker says that, okay, don't worry, I'm fine. Now you see that if you want to know that the person was actually sad, then you have to capture the visual, the visual expression of that particular speakers. Or also when the speaker has spoken this, that acoustics information, the speech variations will have to be captured properly. So this shows that the multimodal information, multimodal inputs actually help to decipher the underlying affects information accurately. Now, how do we develop this system in the next slide? Yeah. So it was a 2018 work. At that time, what we did is that we represented the text, the acoustics, the speech informations. Then we pass it to the bidirectional GRU, and then we try to find an attention between the text and the visual modality. So we call them as a contextual intermodal attentions, in order to capture that which textual part is actually corresponding to which visual part is actually corresponding to the speech part. So every pair we consider text versus visual, visual versus text, acoustic versus text, and then we applied the attention. We created the three set of attention vectors, and then we also capture the attention based on the context that is appearing on the context that appears with respect to a current occurrence. And then we perform both the tasks of sentiment classification as well as emotion recognition. For sentiment, we consider only positive and negative, whereas for emotion, we consider anger, disgust, fear, happy, sad, and surprise emotion. Now, the next slide. Yeah. So you see that we actually use a very well-known data set that Emoji AI, the multimodal opinion, sentiment, and emotion intensity data set. And if you look into the results of these standard benchmark data sets, so in the next slides, yeah. So the result shows that how this MTL is the multitasking learning for sentiment classification also improved in every modality, whether it is text, whether it is audio, whether it is video. Emotion also, we observed improvement in every modality by developing this multitasking system, because emotion helps the sentiment and sentiment also helps the emotion. So if you can effectively share this information between these two tasks, then we can improve the performance. Now, then we have some other matrices also, that for example, when the text, how text and visual, when the second sets of result, you see that T plus B, T plus A plus B. This shows that how the two modalities helps compared to a single modality. In the third column, like T plus A plus B, it also shows that how three modalities altogether helps compared to the other modalities. Now, as a consequence of this, now we also try to understand whether sarcasm detection obviously is a very hard task, and whether it is related to sentiment and emotion and how it is related. So if you can model the sarcasm, sentiment and emotion all together in an end-to-end framework, how they can help us. So in the next slides, so these are all the results you can see, and then you come to the final next so analysis, and then maybe in the next slides. So this is what the sentiment and emotion, whether it helps, and this was in the SEL 2020. And the main idea was that if you know the sentiment, if you know the emotion, then whether these two can help in detecting the sarcasm for sarcasm detection. We actually used the existing data sets that was released at that point of time for sarcasm detections. Upon next slide. So the data set was known as the master data, and it was very small data, multimodal data with video, audio as well as text. And what we did is that this particular data was only for sarcasm. We de-annotated it with the sentiment values as well as the emotion values, and then we tried to show that how these two actually help in sarcasm detection. We came up with two important attention mechanisms. One is that we call them as an intersegment intermodal attentions and intersegment intermodal attention. I will explain it briefly with an example what we mean by this. And also this was based on that GRE framework, text, acoustics as well as visual information where features were extracted, and then we, through these two very novel attention mechanisms, to combine them together, and then we perform the different tasks. Now, if you want to understand, let's see how this the attention mechanism works. Okay? The idea is that if you divide the text, the text features, for example, you can see then the audio features and the visual features, and all these features we divide. That means the feature vector we segment into smaller units. Okay? And from this smaller unit, we actually what we do is that we apply a kind of attention between this model. So that now the attention is not at the whole feature vector of text utterance with the feature vector of the audio. Rather, the vector is broken into smaller segments, and then we try to find out an attention for each of these segments across the different modalities. On the other hand, the intersegment intermodal attention, we actually divide the representation into various segments, and then you combine them together. Now, what is the combination mean? That every time step, let's say that what was the text representation, what was the audio representation, or what was the visual representation. We take only those representations, we concatenate them, and then we apply the attention between them to understand that how this the attention actually works, intersegment attention actually works. So these two actually are found to be very useful to capture the relationship between the different segments across different modalities, and also to capture the relationship between the different segments within the modality. Now, this actually we experimented with this data that we have taken and expanded. In the next slide, also there were cases where implicit attention and implicit annotation and explicit annotation, because sarcasm detection is a difficult task. You really cannot always detect the sarcasm based on the current utterance. Okay? Context will be useful obviously, but sometimes your common sense knowledge, the background knowledge sometimes may be also useful. So if the background knowledge is useful, then it was known as that implicitly it was sarcastic, but you need an extra knowledge to decide that it is actually sarcastic. But explicit means there will be explicit marker that will give you a guidance about the type of that particular utterance, whether it is sarcastic or not. So these are the details that we take the data from different TV series, and then we have actually done extensive evaluations, qualitative evaluation, quantitative evaluations. Can you go to the next slide? Yeah. So you see that next slide. Yeah. So you see that again that we found that how the sarcasm was doing for single touch learning, and then when how sentiment helps for sarcasm detection, how emotion helps for sarcasm detection under the MTL framework, and how sentiment and emotion both help in the sarcasm detection when all the three tasks are performed. And we did it both with respect to the speaker dependent information, where the speaker information is also made available, and in the another setup where the speaker information was not made available. And we do it by and then show that statistically how they are significant. Later on, we also converted this into the generation task, that how this can generate a response that comply with next slides here. Comply with the underlying sentiment and emotion of the speakers. For example, this is one of the work we tried to build the multimodal dialogue systems for response generation based on the sentiment and emotion. So please go to the next slide. Yeah. So this is basically nothing but it's not a classification problem, but it is a generation problem where you are generating the response, you have to capture the affective information of the speaker from the utterance, textual utterance, from the acoustic features, as well as the visual information. And all these information will have to be used for generating the appropriate responses. Okay, and then we have, because such kind of data is not readily available, so what we did is that we created our own data for this particular task. Okay, so we'll go to the next slide. So this is how it is happening. For example, every utterance, how they are labeled in the different sentiment, whether and the emotional information, and how actually these actually are used to generate the next response. And it is because time is not there much. This can move. Yeah. So maybe there are other things. For example, we curated the data from comedy as well as drama from the TV shows. There was we annotated it by semi-supervised manner, and then we created a handsome amount of data sets for performing this task. And please next slide. Yeah, please next slide. So you can skip this Arpan. Now you can come and let's see now that how particularly the classification problem in recent time, the sarcasm, sentiment and emotion, that a paper that we published in ACL 2020. So we try to implement the ideas in using the quantum. So how it was implemented, we'll very briefly show you. Maybe Arpan, you can go to the slides and then maybe you can show that how it was implemented so that to establish the connection. So you can skip this part maybe later on. Yeah. Let's start with quantum one.
So, as Asif has mentioned, that all of these things in multimodal and multitasking framework is imperative, because without the presence of a single modality, our model might not be able to correctly identify our task, be it sentiment, sarcasm, or emotion. So, in this lecture, we'll be presenting one work that we have published recently in Transactions in Computational Social Systems. The main task of it was to propose quantum circuits in natural language processing. But before that, let me briefly intuitively explain where quantum fits in this particular problem definition. So let's say if I give you the word bat, B-A-T, in this particular time step, the bat word can either mean the mammal or the sports equipment cricket bat. So as you can see, in this particular time step, a single word can mean two very different things at the same time. So we propose that such relation or word homonymy can be better captured by quantum superposition. And later on, let's give you the example of sarcasm. So let's say someone gives a statement that he or she loves to take a cold shower at 3 a.m. during winters. So due to the presence of word love, one might assume that sentence is a positive sentiment. But if you introduce additional modalities like the voice tonality or the facial expressions, you will understand that the sentiment was negative due to the presence of sarcasm. So as you can see, there's a very clandestine interplay between these two modalities in order to bring about actual information that the person is trying to share. So this interplay between these modalities can be captured by quantum interference as well as entanglement. I'll briefly explain what these mean in later slides, but that's the basic intuition that we propose in this particular work. Now, additionally, in the classical framework, we understand that designing multimodal and multitasking frameworks is quite challenging, because in this time, people were basically relying on deep neural networks, binary TMs, and even attention frameworks to correlate the three modal information together for the model. But these are highly computationally intensive, and the results leave much to be desired. Like the accuracy and the performance that you have observed are not quite great. So we also propose that maybe superposition, entanglement, interference, as well as measurement property of the quantum circuits will be helpful in this problem. Additionally, we also observe that training classical deep neural architectures that have over 2 lakh or so million parameters are quite computationally expensive. So we also say that if you exploit these superposition, entanglement, interference properties, it will be getting competitive performance at a lower computational cost. That was a brief idea. Now, let me just give you all the terminology that we are using during this paper. First is the qubit, entanglement, interference. What I mean by those, the gates that I'll be using. What do I mean by noisy scale, intermediate quantum computers, as well as lastly the variational quantum circuit. Now, this VQC is actually an important part because this plays the key role in our hypothesis. So basically, the qubit is the smallest building block in the quantum domain, and it has the phenomenon of superposition, wherein, as you can see, as compared to classical bits, which can either be 1 or 0, qubits can either be 0 or 1 at the same particular time. So in this intuition, we can say that let's take the example of bat again. So let's say at a particular time step, the bat is a mammal as well as the sports equipment. Now the presence of additional context surrounding the word, the probability of the word lying on either cricket bat or the mammal will vary. So this property is aptly captured by the superposition property of the qubit. So a few more attributes, spin up and spin down. So superposition means that an electron can either be in the spin up state as well as spin down state at the same time. So there is no state 0 or state 1. Rather, in qubits, there is either spin up or spin down state. Now, in quantum computing, we denote the spin up and spin down state using matrices. So this is the configuration of the spin up, spin down state matrices. And this corresponds to the classical bit 0, because since we'll be using quantum computers, then this quantum state has to be mapped to a classical bit for further processing. So this spin down is then a map to classical bit 0, and spin up, which is the configuration 01, is mapped to classical bit 1. Now comes the qubit measurement. So as you can see, qubits are in superposition and entanglement. Now in order to map them to classical bits, we need an apparatus. Now that apparatus is basically a matrix that, depending upon the alignment, will get varying results. So if this electron, let's say electron qubit, is in superposition and we perfectly aligned, then we'll get the exact same result. So it is in spin upset, as you can see from this architecture, we get the proper result. But if it is slightly skewed or parallel, we see the results vary depending upon the angle of the apparatus. Now, as you can see, the apparatus can either is a simple matrix. It can vary, and depending upon the qubit state, we can measure the state of the quantum system using this equation, which is basically the inner product of the apparatus with the qubit. So as you can see, this qubit is state up, we get the result 1. Now a few more things is that to denote such matrices, instead of let's say it's just a single qubit, so we are okay with just 2 states. But if it is a, let's say 5 qubit or 10 qubit states, so we need to do about 10 different instances in this matrix, and it will be huge work to write them on paper. So rather we use the bra and ket notations. So this bra notation, which is denoted by the angular braces followed by the matrix and the OR line, it denotes it is a quantum complex conjugate of the matrix, and the ket notation is simply the matrix itself. So if you see this notation somewhere, which is bra A and ket E, it basically means that A transpose is multiplied by the matrix E. So that's it. And also, if you see this notation ket 1, this basically means that it is a spin up state corresponding to 0 and 1. And if you see a ket 0, this means it's a spin down state with 1 and 0 configuration. Now, how does bracket notation make our life easier? So let's say, as you can see, this is just a single qubit system, and then that qubit is in superposition with spin down and a spin up state. So if you expand this, we have to write it like so. But if you simply use ket and bra notation, everything makes a lot more sense, and it's quite neater and takes less time to write it down, which is why bracket notation is useful. Now coming to multi-qubit system, so these 0, 0 and 0, 1s, as you are quite familiar, these depend upon the binary notation of numbers. Now we can use these states and map them to quantum world like so. So this 0, 0 state or ket 0, 0 is given by the ket 0, the tensor product with ket 0, or basically the second qubit. So if you expand this ket 0, we know it is 1, 0, tensor product 1, 0, and the tensor product between these two matrices give us this result. For those of you who don't know what a tensor product is basically you multiply every element in this matrix with every element in this other matrix and just list down the result. So it is 1 times 1, 1 times 0, so 1, 0, and 0 times 1, and 0 times 0, which leads to 0, 0. Same thing here is a tensor product between states 0 and state 1. You get the result 1, 0 times 1, 1, which is 0, 1, and followed by 0, 0. And all of these different states can be mapped to 2 qubit system like so. Now, one other thing, so basically as you see, the state 0, 0 is denoted by this particular matrix configuration, which is 1, 0, 0. On the other hand, 0, 1 configuration is represented by this matrix value 0, 1, 0, 0. So basically, in short, the first value of a matrix denotes the probability of a qubit lying on the state 0, 0. The second one will give you the probability of the qubit falling into state 0, 1, and so on and so forth. Now, if I give you the matrix 1 by root 2, 0, 0, 1 by root 2, this means that my qubit is in state 0, 0, ket 0, 0, as well as ket 1, 1 with probability 1 by root 2. This is what we'll understand if you see matrix like so. Now coming to the entanglement interference, as I have said in the sarcasm example, the presence of a single modality might flip or interfere with the sentiment polarity or sarcasm polarity of a particular sentence. So this is what it's meant by quantum world. Entanglement qubits always correlate with each other to form a single system. And then in interference, qubit states can interfere with each other because each state is described by a probability amplitude, just like the amplitude of width. So by this definition, we can understand what you mean by entanglement interference in the quantum world. But for intuitive explanation, you have to relate it using the sarcasm example. So because two qubits are in correlation with each other, and they have the capability to interfere with each other. So in this qubit, if you take let's say qubit 1 is your text modality and qubit 2 is your video modality, they have the capability to correlate as well as interfere with each other, thereby leading the hypothesis that these characteristics of quantum system can aptly capture the interplay between the different modalities together. Now, in quantum computing, there is also that measuring of the state of one of the qubit allows us to know the state of the other without needing to measure it. So, to better explain this, let's say I give you two boxes. One box has a cube, the other has a cylinder. Now, let's say I toss a parcel, one box to India, and you are left with the other box. As soon as you open that box and you find, you will be able to understand that what the parcel box held without needing to verify it by yourself. So this means if you measure just one qubit, you will immediately know what the state of the other qubit is. And then the interference property also has the capability of destructive as well as enhance amplitude difference, like the double slit experiment that you're so familiar with. Right, now coming to quantum gates, these gates are what I used in my work. There are many other gates. So basically there's Hadamard gate, there's NOT gates, CNOT gates, Pauli gates, which introduces rotations in X, Y, and Z axis. There's the phase gate as well as the measure. So I'll explain what these gates are and as well as the matrix configuration like so. In the NOT gate, which is denoted by X, the matrix configuration for this gate is given by 0, 1 and 1, 0. Don't worry if you don't exactly remember what these matrix configurations are, because in varying literature, the matrix values actually differ. But essentially, they do the same thing. So let's say if you apply the NOT gate to a get 1 qubit, then it is flipped to the state 0. Similarly, if you apply the NOT gate to qubit 0, which is in state spin down, will be in spin up state. Now by default in a quantum circuit, all of the qubits are initialized to get 0 by default. Now coming to Pauli gates, in the Y gate, which introduces rotation in the qubit in the Y axis, it is given by this matrix configuration, and for Pauli Z, which introduces rotation in the Z gate, there is this configuration. And then because it is simple rotation, the value of the qubit does not change. What changes is the phase values. Now coming to Hadamard gates, and the Hadamard gate is represented by this value, which is 1 by root 2 and this matrix configuration. And if you apply Hadamard gate to a cat 0's qubit, you will get the result like so: cat 0 plus cat 1 with 1 by 2, which upon expansion you will find this result, which basically means that the qubit is now in state 0 as well as state 1 with equal probability. So basically Hadamard superimposes a qubit into its different states, and then yeah, that's it. Coming to the CNOT gate, this actually stands for controlled NOT gate. That means this CNOT gate accepts two qubits. The first qubit will be the control gate, which actually determines if the CNOT gate will flip or will not flip the polarity of the second qubit. So, and this is given by this matrix. As you can see, the first qubit is the target qubit. That means the CNOT gate will act upon this particular qubit, and if the CNOT gate will act or not will be determined by the second qubit, which we call the control qubit. Now, if this control qubit is 0, the state of the target qubit is not flipped. But if it is 1, it is flipped. As you can see, like the matrix equation multiplication is highlighted here. You can follow along. You just multiply it as you do in an inner product, and you will find that the state this state is maintained after the application of CNOT gate because the control qubit was 0. In this case, since it is the control qubit was 1, the state 0 is then flipped off 1, as you can see here. So basically, the control NOT gate stands is dependent upon the value of the control qubit, and based upon the value of the control, the state of the target qubit is flipped. And a few more examples for each of these states have been highlighted here. Due to time constraints, I'm skipping these. Right. Now another property is that as we have already seen how does Hadamard gate transform a qubit into superposition. We just do inner product and we'll arrive at this, which is in 50% spin up as well as 50% spin down. But if you combine Hadamard and CNOT gates together, then the qubit is now in superposition as well as entangled state, as you can see from here. So in this state, you can see that the qubit is in state 00 with equal probability, and as well as in state 11 with equal probability. So using Hadamard and CNOT gates together introduces superposition as well as entanglement to the quantum circuit. Now, what I mean by noisy intermediate scale quantum computers is that during this work, as you can see, right. So here, this is the IBM Cube Hasm simulator. It has 1 qubit and simulated qubits up to infinity. Now, here these actually are actual quantum computers that have been made public by the IBM company, and but each of these quantum computers have quite a few qubits, like very less. There are 5, 15, 1, and 5. Now, as of right now, these qubits has been increased, but during this time, the amount of qubits available was very less. Now, this is why we mean by intermediate. Like, we cannot simulate huge complex tasks into these quantum computers due to the lack of the qubits, and they cannot handle complexities that will require more qubits than 5 or so. And these numbers from 751 to 76, this denote actually the amount of jobs that have been scheduled before you. So let's say if you want to schedule some job to this IBM Q Santiago, you'll have to wait for this 26 job to finish, and then your job will then be plugged onto the quantum computer. Now, now I'll explain what I mean by noisy in this case. So in this circuit, as you can see, there is a Hadamard gate that's been applied to the qubit 0, as well as a control NOT gate where the target is Q1 and the control is 0. So based upon the value of Q0, the C0 gate will flip the value of Q1. And these are just the measurement gates or the apparatus that will measure the value of this qubit and then map them to a classical bits here. Now, upon this implementation, we can assume that since we have Hadamard and control NOT gate together, then we expect superposition as well as entanglement, which basically means that we require this matrix as a result, which means that the state 0, 0 will have some probabilities as well as state 1, 1 will have some probabilities, while the intermediate states like 0, 1 and 1, 0 we have no values there. This is what we expect, and this is the result we get on the Chasm simulator on that particular circuit. If you ran it for a few times, then this is the expected results, and you can see the state 0, 0 has a probability and state 1, 1 has a probability, while the intermediate states 0, 1 and 1, 0 are left with no probabilities. That means during the experiment, these states were never triggered. This is what they expected. This is true. But when we run the same circuit on the IBM Q Lima quantum computer, we do get a huge probability for state 0 and state 1, but the some probabilities are present for 0, 1 and 1, 0. These are the noisy information that are inherent to a quantum circuit. This is because we act upon subatomic particles or electrons. So in the quantum computer, slight change in vacuum, temperature, or even the electromagnetic field in action will lead to degradation, which leads to this noisy information coming up in actual quantum computers. This is what I mean by noisy. So basically, noisy means that irrelevant states come up due to the quantum noise, and intermediate means the lack of available qubits for our purposes. So at this work, only noisy interphysical quantum computers are available for experiments. Right, now comes to variational quantum circuits. So this means that these circuits are actually parameterized. So basically, let's say you build a circuit, but so let me give you an example if I have. Okay, so variational quantum circuits are parameterized quantum circuits where quantum algorithms depends upon free parameters. So to give you an example, remember in the Pauli rotation X, Y, and Z gates, we understand that rotate the qubits in X and Y axis respectively, but how do you determine the angle of rotation or the amount of rotation to induce? Do you rotate by 2 degrees or so and so forth? So these Pauli X, Y, and Z gates are actually parameterized. Rather, they're free. They can be let's say optimized based upon our task, which I'll explain later on the slides. And they are trained by a classical optimization algorithm that makes queries to a quantum device. This basically means, in layman's terms, since these parameters can be optimized, you initialize the Pauli rotation to some random value, you run the circuit, you get some results, you compare them with your goal labels, you get some loss, and based upon this loss, these degree of rotation can be optimized. So this is what we mean that because of these free parameters, these quantum circuits are now optimizable in an end-to-end fashion with classical algorithms. This is why VTC are very important in quantum natural language processing. Additionally, the optimization is usually an iterative scheme that searches out better candidates for a parameter theta deficit. This means that let's say you rotate a particular qubit in x-axis by 2 degrees and you get some value. So based upon that value, you get some loss, and then you update it to, let's say, instead of 2 degrees, you rotate it by 10 degrees, and you get the result which is better in that case, as you can see, iteratively, we can determine the value of theta, or basically the degree of rotation on the polygates. Now, the dataset for the work was mastered extended. So, as Sir briefly described, in this dataset, there was sarcasm class labels. So, it's a multitask dataset, which means that the dataset has sarcasm, sentiment, which include implicit as well as explicit, and then emotion, which also includes implicit and explicit. So, for this dataset, the task was that we have to build a single model that will be able to identify the sarcasm class, the sentiment implicit as well as sentiment explicit class. So basically, the sentiment implicit has positive, negative, and neutral, as well as sentiment explicit also has positive, negative, and neutral. So on total, there are there is sarcasm, sentiment implicit, explicit, emotion implicit, as well as emotion explicit task for classification. And then the dataset has 3.68 hours of total videos with 690 samples in the total dataset. Now, how we propose our model is that we took the game plan of the paper as proposed by Dushan Singh Chauhan in ACL back in 2020. So we basically took exactly the feature preprocessing he has done. So basically, we don't make much any changes. We feed each of the text for sentiment polarities through the concatenation layer, where we concatenate the context as well as the utterance text. We pass them for dense layer for reducing the dimensionality of the text features. We pass in the acoustics layer for the similar dimensionality, and then we pass the visual layer for the context as well as utterance through dense layer for the same dimensional layer. Now we take these embeddings, let's say, of text, acoustics, and visuals for our purposes. We let go of his inter-attention and inter-curricular attention that he has proposed in his paper, and we simply use these embeddings for our purposes. Now, this was the circuit that we have proposed. So, as you can see, the concatenated features of text, acoustics, and visual modalities that we have taken from the game plan of the previous paper. We pass them through a dense layer. So, this dense layer will has 150 neurons, 75 neurons in the hidden layer, 37 neurons in the second hidden layer, followed by the three nodes in the output. So basically, it will be it has 75 times 150 plus 1 plus 75, which is I guess it's around 11,000 or so, followed by 37 times 75 plus 1 plus 37, which should give you 5,000 or so something. And finally, the output layer will have 3 times 37 plus 1 times 3. So this is around 100 or something nodes. So like I'm not on math whiz, but it should give you around 14,000 parameters in total. So the whole model here is only the amount of trainable parameters is around 14,000, which is vastly less as compared to the other classical methods out there, which I will show in soon. So what we do is that these concatenated feature modalities are then passed through this dense layer in order to reduce the dimensionality. Now, why do we need to reduce the dimensionality? Is because the quantum circuit that we proposed only had 3 quantum trainable parameters. Right, as you can see, theta 1, theta 2, theta 3. So basically, this dimensionally reduced feature set are then plugged on to these 3 trainable parameters. And these trainable parameters induce rotation in the quantum circuit. And then based upon the rotation and the result we observe, we measure the expectation, which is basically the states, which is, let's say, 0, 0, 0, 1, 0, and so forth. These states are multiplied with the probability achieved. So let's say the expectation in this state would be the state 0, 0 multiplied the probability 0.483 plus state 1, 1 multiplied the probability 512. This is how we calculate the expectation in quantum circuit here. And so based upon the expectation value, we pass them to the 5 different output layers, each for the different tasks. So the first task was the sarcasm, the second task was sentiment explicit, third task was sentiment implicit, fourth task was emotion implicit, and the fifth task was the emotion explicit layer. So as you can see, just one value is able to identify all of these different tasks. So there is multimodal because of text, acoustic, and visual, and there's multitask because of these various tasks at once. Now, so here we now show the actual makeup of what this variational quantum circuit was that we proposed. So this was the single gate cluster for the variational quantum circuit. It was initialized by Hadamard gates So basically, the quantum circuit had 4 different qubits and 4 classical bits for measurement purposes. So the first qubit was operated upon by a Hadamard gate, and the fourth qubit was also operated upon by the Hadamard gate, followed by a phase gate, which are responsible for changing the phase. This will not introduce vibration in the qubit, rather it will simply change the phase of the qubits. And then followed by the CNOT gates, which will ensure entanglement between each of these qubits in the whole system. So this configuration of CNOT gates is on design, because if we simply apply a CNOT gate between Q0 and Q1, this will ensure that only qubit 0 and qubit 1 are in superposition, while the rest of the qubits are independent. So in order to ensure that this qubit 1 and qubit 0 and qubit 1 are entangled with qubit 2, we also apply a CNOT gate with the control value of qubit 1 and the target of qubit 2. This ensures that the qubit 1 and qubit 2 are entangled together, and so on and so forth. Lastly, these are the rotation gate blocks that we have come up with. This is upon here various hit and trial methods. We tried different configuration for rotation, but most of them did not work out. The accuracy was lacking, or some other problems happened. So which is why after final experimentation, we came up with this particular rotation for this particular task. This is not to say that for every task out there that you want to apply a variational quantum circuit, this particular configuration will work the best for you. It's not actually. In quantum circuit, the amount of qubits that you have, the positions, or the what gates you use, number of gates you use, number of gate clusters that you use, all of these are hyperparameters. So you have to actually come up with some equations that will guide you towards your optimal circuit for your particular task. Right? So as I've said, there are just 3 trainable parameters for this circuit, which are responsible for the degree of rotation in the circuit itself. And H denotes the Hadamard gate, P denotes the phase gates, RZ denotes the poly Z gate, Rx denotes the poly X gate, and Ry denotes the poly Y gate. So Rz is the Z rotation, Rx is the X rotation, Y is the Y rotation, so on and so forth. Now coming to the values, we know that Hadamard gate does not accept any parameters, because simply it uses superposition. So, but the phase gate changes the phase of a qubit, so it is a trainable gate. Now the value of this trainable parameter is denoted by so. We pass for the first phase that is plugged into the qubit 0. We pass the first θ1 parameter, trainable parameter, and we normalize it by the value of all the 3 parameters. So essentially this is given by like so: 1, 0, 0, and e to the power I, followed by the value here. And based upon this matrix, the phase gate changes the phase of qubit 0. Now in the second phase gate, we take the value θ2 from the trainable parameters. Again, we normalize it, which gives us the equation 1, 0, 0, e to the power I, and this value here. This will change the phase of qubit 3 but with this value. And lastly, phase 3, again we take θ3, normalize it, and it gives us this matrix configuration. So this ensures that the phase of the entangled qubits are changed by this value. Coming to the RZ gates, the first RZ gate field gates here are passed with the same value. So basically, all the 4 qubits are rotated in the Z gate in the same value here. Again, this is not a rule of thumb that you have to rotate each of these qubits with the same value. You can plug in different values to each of these gates and see where it lends you. For our purposes, for this particular task, this configuration gave us the best results, so we went with this. So the value of RZ is given by this. We take the sum of all the 3 trainable parameters, we divide it by 3, and this gives us the matrix equation e to the power I, the value, so on and so forth. So with this degree of rotation, these RZ gates rotate each of these qubits in the z-axis with this value. Similarly, this last RZ gate is then simply passed the value θ3, and it rotates each of these qubits with this value. Similarly, in Rx, we pass θ1, so the Rx equation is given by cos θ1 by 2 minus sin θ1 by 2 minus sin θ1 by 2 and cos θ1 by 2. So this is actually defined in the literature. I did not come up with this matrix equation myself. Rather, this Rx gate will denote that whatever value you pass, that the rotation in the x-axis will be carried out by this value that you calculate here. And same for Ry gate. So the only difference is that the iota sign is separated in this matrix. And lastly, this is just a single gate cluster. In order to establish a deep variational quantum circuit, we repeat the same gate cluster 3 times without any changes. And lastly, we measure the value and map them to the four classical bits that you have seen here. And based upon these values, we proceed with our final analysis, which is the classification for the multitask architecture. Now, the experiment setup for the study here was using the IBM-Q experience, which enables you visual UI-based design of quantum circuit. So all of these you can. There's a very user-friendly graphical interface where you can simply drag and drop each of these gates into this quantum in these qubits, and then you can see the results simultaneously. And then we have used the Qiskit Python library, which enables you to connect with the IBM-Q backend. And this enables you to run your algorithms and quantum circuits in the spider simulators or the actual quantum computers developed by IBM. So for this particular work, we have used the QASM simulator and the IBM-Q Pelham for our purposes. Then, the training has happened for 50 pops, and we save the weights, and then we load the weights for the VQC experiment. So this is the results table where we can see that these two are very state of the art before this. So although we did not know the actual weight parameters for this work, it is not reported. We know that the intertension framework developed by the baseline paper that we had used for our getting the embeddings had over 25 lakh parameters. Comparatively, our proposed architecture, which relies on quantum circuit, has only 14,000 parameters. So there is a vast difference in the parameter size, and because of this less parameter, it is also computationally efficient. We don't need to rely on fast GPUs to train. It's simple. GPU will, let's say 1080 Ti is able to handle our model weights and will give you the results in a record time. Now, in the first work, it only had the sarcasm dataset, did not have the multitasking property as we have for our work, as well as the baseline that we have looked at. Now, the accuracy, as you can see, there's around 3% accuracy across the matrix. So our hypothesis that superposition, entanglement, interference, and measurement are better able to capture the relation between the three modalities, which will give us a feature-rich quantum embeddings, has hold true. And because of the lack of trainable parameter size, the model was trained in less time as well. Although I did not report in the table, but the actual time taken for training as well as inference has been reported in the paper itself, and you can check those out. Now, we also ran some ablation studies wherein, one might argue that in this particular model, all the improvement in results that you have seen might be because of the presence of this simple deep neural network. Rather than this VQC playing an important role, this layer is doing the most of the task and giving you a very good embedding, which leads to a better output result. So in order to ensure that this is not so, we perform the ablation study with a purely classical neural network. In this architecture, we had removed the variational quantum circuit. So there's just a input embeddings, which is passed on to the dense neural network and then passed on to the classification for the multitask. As you can see, the results drop drastically across the matrix. Now, we propose the variable quantum circuit into this classical network, but instead of the 3 quantum trail parameters, we just give a single trainable parameter. So we see the results improve quite a bit. We proceed on to the 2 quantum trail parameters. We see the results improve further. Besides this precision, where it basically dropped quite a small amount. And finally, the 3 quantum trail parameters, which is the full architecture that we have proposed, we see the best results so far. Now, this goes on to show that the number of parameters that you have in your circuit enables the model to better capture the relation between the 3 modalities. The more quantum trail parameters you have, the more well generalized circuit you end up with after training. So, in conclusion, we state that our let's say hypothesis of variable quantum circuit enabling better quantum neural network processing has been verified, and our models were processed state of the art by at least 3.7% across the matrix. It's because of the hypothesis of relying on superposition and determinant interference in quantum machine learning. We have just 14,303 tail parameters versus the 25 lakh parameter here, and because of the presence of the ablation study, we are confident that the VQC plays a very important role in the performance improvement, and it's not simply the presence of the deep neural architecture that we observe the improvement. And then increasing the number of quantum trailing parameters might improve the accuracy, because again, such a single task of multimodal multitask neural network, and this increasing quantum trailing parameters might not hold true for various other domains. So we just say that for this, increasing training parameters might improve the accuracy. And these are the references that I've used so far. And thank you for your attention.
Thank you very much, Asif and Arpan.
Long live India and France friendship.